Welcome to a video lecture on the interference of light, covering Young's double slit experiment. This follows along in chapter 27, sections 1 and 2. So please follow along in your textbook. Make sure to take some notes. We will be discussing this more in class. Thank you very much. Here we go. We've already discussed how two waves will interfere with each other when they occupy the same position or point in space. Now, they can either interfere constructively or destructively. Constructive interference means that they combine together, and destructive means that they cancel each other out. Now, one of the things that was shown, and this is from Young's double slit experiment, was the wave nature of light. So that light actually is both, and we'll get into this more, it is both a particle and a wave. It does have wave characteristics. And this property was shown because of this interference that was happening from the double slits of light passing through, which I'll get to in just a second a little bit more. But let's go look at a little bit more on interference. When two waves occupy the same space, they're going to interfere with each other. And here we have a little diagram showing the wave over here on the left, and the two waves interact at point P, where they have two different sources, and it's maybe a little bit tough, but there's the point right there. And since they both happen to be in phase at that point, they will constructively interfere and combine together to create a larger wave. And on the right, we have two waves. Once again, they're from the same, from different sources, and they interact at point P, and they destructively interfere, meaning that they cancel each other out. So this is just it. There are different types of interference, whether you are constructively interfering or destructively interfering. Depends on whether you're adding to create a new wave with a larger amplitude or a smaller amplitude. Thomas Young, in the early 1800s, and he did a bunch of experiments right around the same time, worked to prove that light had wave phenomenon that occurred with it. And one of the ways that he did this was with his famous double slit experiment. And what he would do first is you have a source of light, and you pass it through a single slit, so that way you only have one wavelength of light hitting this the double slit, and this is, so you'd have a slit 2 and slit 1, and then just tiny little cuts in with respect to the wavelength. And what happens is on a screen, if projecting this light onto a screen as it moves through, these two paths of light interfere with each other, and this makes it so that it doesn't act like a particle, because if it was a particle, it would just go straight to the screen and hit the screen, whereas when it actually goes through the slit, it disperses out, and you get this interference pattern, and you have constructive and destructive interference along these different types of fringes, as we call them, or maxima, actually, is a little bit better way of describing it. As Young was able to find this wave nature for light, he determined these areas of maximum and intensity on the screen where there was constructive interference, and minimum intensity where there's destructive interference, and it's based on the two bands of light moving through each slit, and then they hit each other and they interfere. And what he found is the relationship between, or was able to quantify the relationship between the wavelength of light, the spacing between the two slits, and actually the angle of how far away it was based on what maximum or minimum you were looking at. This here is for Young's double slit experiment, showing the interference and the angle for the bright fringes, or the maxima. And it's related to where m is a constant, it's an integer value, and if it's 0, then the angle is 0 because it's straight across. But if it's, as you move up, it depends on the wavelength and the distance between the two slits themselves, that spacing distance. And as you increase maxima and minima, you move, as you increase maxima, you move further out in a greater angle. Now, one of the things here is just understanding, and I'll show you the second formula, which looks at the minima, but it's just the same idea that you're adding a half a wavelength, because it's just going to be 1/2 further on. So it's really not too tricky. So here we have the equation for where the minima, or the dark areas, dark fringes, are located with respect to the angle. Now, this is, as you're seeing, you're just adding half a wavelength, because as you move along here, the integer value times the wavelength just means it's moving further out within that kind of the spectrum, or that diffraction grading that's showing up there, or that the interference pattern, excuse me, that's showing up on the screen. So you can solve this from here and from this thing. The other thing is you really only need to use that one formula, the one before this, and just understand if you're looking for a dark fringe, the first one, you just add a half of a wavelength to it at that point. So you can go from there. All right, 3 quick questions. First, I'd like you to define interference. So you can look that up in your textbook. It may not be necessarily in this right section, but you can find it. Second, what's the difference between constructive and destructive interference? And third, this involves a little bit more thinking. What happens to the interference fringes as the viewing screen is moved closer to the double slit? So you have a double slit. It's projecting and creating an interference pattern on a screen. That screen is now moved closer. What's going to happen to that interference fringes themselves? Think about things like, will they get brighter, dimmer? Will they move closer together, get farther apart? Will they get out of focus? Will they fade in, fade out, disappear? Anything along those lines. But just think about what happens to those fringes. Thank you very much. Put these answers in online, and I will see you tomorrow in class.